Hi everyone, welcome to the OneClass channel. Today I'm going to be helping you through some chemistry problems. My name is Marlyn. I'm a second year student at the University of Waterloo, studying chemical physics with a minor in math. And let's get to it. Okay, so our first question is, what is a half reaction? Why must the number of electrons lost in the oxidation half reaction equal the number of electrons gained in the reduction half reaction? And summarize briefly the steps in the half reaction method for balancing redox reactions. What two items must be balanced in a redox reaction? Okay, so the half reaction method is an algorithm that helps us balance out redox reaction. The reason why we necessarily have to break it down using the half reaction method is to ensure that that conservation of mass and energy both occur. And so this means that we want charge to be conserved, and we want the mass, so the individual species, to be conserved. And so the steps is that you break it into the oxidation and reduction. You balance them individually, and then you join them back together again. And so first, write out your half reactions. So your oxidation reaction and your reduction reaction. Step 2 is going to be, now for each half, we would like to balance all elements with the exception of hydrogen and oxygen, because we'll balance them later. Because these two involve like OH minus, H2O, and H plus to balance, and that involves charge, which we're not going to touch yet. Next up, we balance O with H2O. And this is in the scenario that we're working in an acidic solution. If we're working in a basic solution, we technically balance O with OH minus, but we'll get to that later. Next up, we balance H with H plus, and lastly, we balance the charges with electrons. Step 3 is going to be multiplying equations. So this is only if necessary by a factor in order to ensure that the electrons gained or lost, in order to ensure that the electrons cancel out basically in both half reactions. Because we don't want to see them in the overall reaction. And this has to do with, Next up, we will simplify. So you add the two equations back. And simplify by canceling anything that appears on both sides of the forward reaction sign. And lastly, you're just going to double check your species, so your mass species. So double check conservation of charge and conservation of mass. Okay, and if we are working in if we're working in if we're working in a basic solution, the rules are a bit different. What you're going to do is note down the number of hydrogen ions and add an equal amount of OH minus, because in a basic solution, it's not providing us with hydrogen ions, instead it's providing us with hydroxide ions. And yeah, add equal amount of OH on both sides of the equation. And then recall that H plus OH minus is going to give us H2O. So if you see them together on any one side of the equation, just write down H2O and cancel out any H2Os that will appear on both sides of the sign. And that's going to be it. And so if you want to do an example, so we're going to write down the unbalanced ionic equation. So we're going to be having a reaction, a redox reaction between iron 2 plus ions in an aqueous solution plus these ions also in an aqueous solution. Give Fe3 plus aqueous plus Cr3 plus aqueous. And so we're going to write down our separate equations. So for oxidation, we're going to have Fe2 plus in aqueous solution to Fe3 plus in aqueous solution. And for our for a reduction reaction, we're going to have in aqueous solution to Cr3 plus in aqueous solution. Okay, so in this, because this is oxidized, this is going to be what we call this is our reducing agent, and this is our oxidizing agent, because it oxidizes iron, and this reduces this, and this becomes our oxidized product and our reduced product. And so, let's go back to the rules that we have up here to see what we have to do next, because it is an algorithm, so it just tells you exactly what you have to follow in order to ensure that the equation ends up balanced. So next, we want to balance all elements except hydrogen and oxygen. So let's see if we have any elements down here to balance. Iron, chromium, we need 2 of them. So let's do that right now. Let's just put a 2. And do we have any elements after that? Nope. No, we're only left with oxygen, and we know that we can't balance that yet. Scroll back up here, check, and we balance O with H2O. Okay, so because we have 7O here, we're going to have plus 7H2O on this side. And because there are now sort of finished with that step, next one we move to balance H with H plus. Okay, so here there's no hydrogen, but here we have now added 14 hydrogens that we will need to balance. And so let's just actually rewrite this. So let's start with the 14 H plus that we knew about. Plus Cr2O7 2 minus to get Cr3 plus, and we know that we have multiplied this by 2. Plus 14 H2O. So hydrogen is balanced, oxygen is balanced, and the mass species are balanced. So the next thing that we're going to have to worry about is charge. So let's start with the oxidation reaction. And we see that this side has a charge of 2 plus, and this side has a charge of 3 plus. And remember, we can only balance with electrons that are negative. So we're going to add 1 electron here, and we get 2 plus, 2 plus, so that one is fine. On this one, we have a total charge of 12 plus on this side, and 6 plus on this side. So what we're actually going to do is add 6 electrons in order to get an equal charge of 6 plus and 6 plus on both sides. So we're just going to have to rewrite that. Remember, we multiplied it by 2 and added (7H2O) liquid, aqueous. There we go. And so next up we have the charges balanced, mass species are balanced, and next up we want the electrons added or removed to be equal. And that means that we will multiply this equation by 6 before we add it to the next one. So let's just write it down here. And so we have 6 Fe to 6 Fe3 plus aqueous plus 6E minus. And so next we just add these two equations. We know that the 6 electrons cancel. So that's the first thing that we deal with canceling out. And so let's just write the total equation down here. And we get 14 H plus Cr2O7 2 minus plus 6 Fe2 plus to get 2 Cr3 plus aqueous plus 6 Fe3 plus aqueous plus 7 H2O liquid. Okay, and this is going to be our balanced equation. Sorry, let me just rewrite that so that it's a bit clearer for you. Okay, and this is our final balanced redox reaction. So let's just do the final step of double checking. And so 14H, 14H, on both sides, 6 iron, 6 iron, oxygen, 7 oxygen, 7 oxygen, 2 chromium to 2 chromium, and that's it. Again, charge, 14 plus 12 minus 2. So 14 plus 10, that's 24. Here, 6 plus 18, which is 24 too. So we have 24 plus, 24 plus. So mass and charge are both conserved when the equation is completely balanced. If you want to continue, and it's a basic solution instead of an acidic solution, which they will tell you in the question, let's just run through that quickly. Then what's going to happen is here you add 14OH minus. Similarly here, 14OH minus. This becomes 14H2O plus 6Fe2 plus Cr2O7 2 minus to 2Cr3 plus 6Fe3 plus 7H2O plus 14OH minus. Let's cancel out these H2Os, and we get 7H2O plus 6Fe2 plus Cr2O7 2 minus 2Cr3 plus 6Fe3 plus 14OH. So you see all we did was, instead of having positive on this side, we're going to have negative 14OH here, and instead of the 7H2O on this side, 7H2O on this side instead. And it's just because of what the solutions are providing us with. So basic provides us with hydroxide ions, and acidic provides us with hydrogen ions. And that's it. Okay. So next up, we're going to be looking at the decomposition of nitramide in water that has this chemical equation and this proposed mechanism. And we're going to want to determine the rate law for each step. So rate 1, rate -1, because it's a reversible reaction, because it's in equilibrium. Rate 2, and rate 3. And of course, rate overall. And yeah. Okay, so let's start by determining the individual rate laws. And we know that the individual rate laws depend on the reactants used. And so for rate 1, it's called the molecularity. So it's going to be K1 multiplied by O2NNH2, because that's the only reactant in that case. Rate -1 is going to be equal to K-1 O2NNH minus multiplied by H plus. Rate 2 is going to be equal to K2 by the reactant that we have in that equation, which is O2NNH minus. And lastly, rate 3 is going to be equal to K3 into H plus OH minus. And these are our individual rate laws. And so we know that the overall rate law depends on our slowest reactions rate law, and our slowest reaction is going to be this one. The reason why is because the reaction can only move as fast as its slowest mechanism, because you can't have the third mechanism until the second one is complete, which means the reaction isn't complete yet. And so our rate overall is going to be equal to K2 O2 and N H minus. But the problem with this answer, and the reason why it does not look like the rate that's given in the equation, is because this is an intermediate. It's a species that is produced and consumed within the reaction, so it doesn't appear in our overall reaction, which means we can't put it in our overall rate law because it's virtual in a sense. We can't measure it during the reaction, and we need to put down things that we can measure. And so what we're going to do is we are going to use this in order to write it in terms of species that are in our overall rate, that are in our overall chemical equation. And so we know rate 1 is equal to rate minus 1 because they're in equilibrium. And so O2 and NH2 is equal to K minus 1 O2 and NH minus H plus, and then we just isolate for this, and we get O2 and NH minus is equal to K1 O2 H2 over K minus 1, this is supposed to be H plus, H plus. And then you just substitute that right back in here. And we get is equal to K2, K1, O2, and H2 over K minus 1, H plus. And if we decide that K is equal to K2, K1 over K minus 1, then rate overall becomes K O2 and H2 over H plus. And this looks exactly like what we're given in the equation. And so that becomes our final answer. Okay, on to our next question. We are looking for the difference between polar protic and polar aprotic molecules, and it all lies within hydrogen bonding. So in polar protic, we tend to have hydrogen bonded to a highly electronegative atom. And if we just look at the periodic table, so the structure of the periodic table is very beautiful in my opinion, because you have trends across the groups and the periods that you of course learn about in high school, and we have electronegativity increasing this way and this way, which means fluorine is our most electronegative, oxygen is also highly electronegative, and nitrogen is also highly electronegative. And so in the case where hydrogen is attached to oxygen, fluorine, or nitrogen, what happens, let's just write that down here. So it needs to be oxygen, nitrogen, or fluorine in most cases, and nearly all cases that you'll deal with. And the reasoning is because their electronegativity is so high that it virtually almost pulls the entire electron from hydrogen, which leaves an extremely polar molecule left behind. So let's take the example of H2O. So what happens is that because this pulls the electron from them both, it leaves them with a slightly, well, yeah, a slightly positive charge, a slightly negative charge, and a slightly positive charge, but more so than you would have in a polar A product where the atom isn't as electronegative, so it doesn't pull a charge away as much and doesn't cause as strong partial charges. And this is actually the reason why water is such a good solute and is so good at dissolving other things. And it's because of the fact that what happens is, like, let's say we have a positive ion and a negative ion together, like lithium bromide. What happens when you put it in water is because of oxygen's now more than usual negative charge, it's going to be pulled to the positive ion and surround it. So oxygen will be closest and it'll form sort of a shell, completely isolating it from the other one, basically splitting the two away from each other. And that's how you have things dissolve. Yeah. And you're going to have the same thing occur with the negative charge, except now the hydrogen will be strongly attracted to it. So you're going to have a negative charge. Let me just put them in blue. Surrounded by, oh, let's just write down and so that's why water is so good at dissolving things, because it basically attacks it, splits them, and surrounds them, which would prevent them from coming together again. Now, a polar A product is still polar, so hydrogen is still attached to an atom that is more electronegative than it, but not as highly electronegative as oxygen, nitrogen, and fluorine. So it's still polar, it just doesn't have the capability of hydrogen bonding, which doesn't allow it to do all of these special tricks that water does. And a good example of this is actually in our organic compounds, where we have hydrogen attached to carbon. And so let's take the example of acetone. So yes, hydrogen will still have a partial positive charge, and carbon will have a partial negative charge, but not strong enough that it would lead to characteristics like this. Just it would be slightly weak and rely on other interactions like dipole interactions and van der Waals forces in order for things to happen in reactions. Okay, next up we have a calculation chemistry question. Okay, so if we are given the fully balanced equation, the net ionic equation, the volume uses 0.1 of silver nitrate to titrate bay water samples in March. So for the March sample, they use 7.3 milliliters. For the April sample, they use 4.46 milliliters. Using the balanced equation, calculate the average number of moles of sodium chloride in each of the titrated samples. Calculate the average number of grams of sodium chloride in each of the titrated samples. Use the balanced equation to calculate the salinity in parts of each of the samples. It can be assumed the density of bay water is 1 gram per milliliter. So let's just get into it. We know that because of the balanced equation, the ratio is 1 to 1. So if we have the moles of sodium nitrate used, we can find of silver nitrate used, we can find the moles of sodium chloride that we need because the ratio is 1 to 1. So we proceed by finding this. And the moles of AgNO3 are going to be equal to 0.01 multiplied by 0.0073. So this is for the March sample. And this will give us 7.3 by 10 to the negative 5 moles. And that would be the moles of NaCl for this March sample. For the April sample, we're going to use 0.00446 and we get 4.46 by 10 to the negative 5 moles. April sample. Okay, on to the next question. We want to find the average number of grams of NaCl in each of the titrated samples. And so we know that we need is equal to mass over molar mass. So the mass, of course, is equal to moles by the molar mass. Let's just put that down. So for the March sample, we will have 7.3 by 10 to the negative 5 multiplied by the molar mass of sodium chloride, and that's going to be 58.45 grams per mole, and of course this is in moles, so the units cancel, and we get 4.27 by 10 to the negative 5 grams. For the April sample, 4.46 times 10 to the negative 5 moles, again by 58.45 grams per mole. And this is going to give us 2.61 times 10 to the negative 5 grams. And those are our two answers. And lastly, let's move to part C, which is the salinity. And so the salinity is going to be the mass of NaCl over the milliliters titrated. Remember that from March we had 4.27 times 10 to the negative 5 grams. From April we had 2.61 times 10 to the negative 5 grams. And this corresponded to 0.0073 liters, 0.00446 liters. And so we're just going to plug that right back in. And so for the March sample, it's going to be 4.27 times 10 to the negative 5. Sorry, this is supposed to be negative 3. That's just an error in my writing. Over 7.3 milliliters times 1 gram per milliliter. And this is also in gram, times 1,000 milligrams per 1 gram. And this should give us 0.585 milligrams per gram. And we should get the same answer for the April sample. This was also supposed to be to the negative 3. So 2.61 by 10 to the negative 3 grams. All of these is just for the sake of units. That's just so that we get milligrams per gram. So over 4.46 milliliters times, and again, and we again get 0.585 milligrams per grams, which is the same thing as this. And this is our final answer. Okay, so we want to place the species B2 plus, B2, and B2 minus in order of increasing bond length and increasing bond energy. So in order to do this, we're going to need to write out their molecular orbital diagrams. And so we'll have B2 plus here, and B2 minus. Let's just separate these so that it's easier for you to distinguish between them. Now let's label them. So these are 2p. Let's start with our atomic orbitals. These are 2s, 2s. So our first sigma, our first antibonding sigma, our first pi, our second bonding sigma, our first antibonding pi, our second antibonding sigma, labeled similarly for the rest. And let's just start with B2. So let's start by putting in our atomic orbitals. So 2 there, 1 for each, which means B2 minus will have an extra one. So 2 there, 1 for each, plus an additional one. B2 plus will lose 1. So 2 there, 1, no second one. Okay, now let's combine them into our molecular orbitals. So we get 2 here, and just 1. 2 here, we have 2, so we're going to have 2. 2 here, and we have 3. So 1, 2, 3. Okay, and so our bond order is going to tell us about the bond length and the bond energy. So first let's find the bond order for each. And we know bond order is equal to bonding orbitals minus antibonding over 2. So for this one, we have 1, 2, 3. So we're going to have 3 bonding minus 2 antibonding over 2. That's going to give us 1 over 2. Here, we're going to have 1, 2, 3, 4. So we have 4 bonding minus 2 antibonding over 2. And that's going to give us 1. For this last one, we have 1, 2, 3, 4, 5. So we're going to have 5 bonding minus 2 antibonding over 2. And that's going to be 3 over 2. And so now we need to determine the relation between the bond order and the bond length, and the bond order and the bond energy. So we know the higher the bond order, the shorter the bond length, which means the higher the bond energy. Bond order just refers to like how many bonds you have. So in the scenario where it's 1, it would just be 1. So for example, in the case of H2O, has a bond order of 1 bond, 1 bond. If it's 2, then you're going to have a double bond. So that would be like here, where you have a double bond. And that double bond will be shorter, which means that the 2 are closer to each other, which means that there's increased repulsion between their nuclei, which means less stabilization, which means more energy. And so, if we want to list them first in order of increasing bond length, that would mean decreasing bond order. So that means increasing bond length equals decreasing bond order. So we're first going to have 3 over 2, which was B2 minus, B2, B2 plus. So 3 over 2, 1, 1 over 2. And if we want an order of increasing bond energy, that would mean increasing bond order. So it would actually flip. So we go from 1 over 2, so B2 plus, B2, B2 minus, 1 over 2, 1, 3 over 2, 3 over 2, 1, 1 over 2. And that's it. Okay, this one is an interesting one because it applies to the real world a bit more, especially in today's age of climate change. So we are going to be calculating, so assume a car burns octane with a density of 0.692 grams per milliliter. Write a balanced equation for the combustion of octane to carbon dioxide and water. And if a car has a fuel efficiency of 22 miles per gallon of octane, what volume of carbon dioxide at 25 degrees Celsius in 1 atmosphere is generated by the combustion when that car goes on a 75-mile trip? Okay, so let us begin with the first question. We have C8H18 plus, we're going to fill in a number there, is going to give us 8 CO2, so we want to balance the carbon first, and we want to balance the hydrogens too, so that's going to be 9 H2O, and then we come and we balance the oxygens, so this is going to be 16 O plus 9 O, that's 25 of them, so we're going to need 25 over 2 O2. 25 over 2. And this becomes the balanced equation for the combustion of octane. Next up, we deal with the harder question. So a car has a fuel efficiency of 22 miles per gallon. What is the volume of carbon dioxide used on a 75-mile trip? So first we want to calculate how many gallons we use. So we're going to do 75 miles over 22 miles per gallon. And that is going to give us 3.409 gallons of octane. We want to convert this to moles in order for us to find the moles of CO2, and then we convert those moles of CO2 using the ideal gas equation into a volume. And so, to convert to moles, we're going to do 3.409 gallons multiplied by 3785.41 milliliters per 1 gallon multiplied by 0.692 grams per milliliter. So we want to convert it to milliliters so that we can find the grams. And then finally, we want to divide the grams out. So we have 1 mole per 114.25 grams. All of these values you should be able to find on the internet using some chemistry resource. And this will give us 78.177 mole of CO2. This is given in the question. And so now we know the ratio is 1 to 8 according to our balanced equation, which means that we need to multiply this by, of octane. We need to multiply this by 8 to find the moles of octane used. Moles of CO2. So this would be 8 by 78.177. And this is going to give us 625.414 moles of CO2 used. And next we're just going to use the ideal gas equations to figure out what that volume is. So PV equals nRT, which means V equals nRT over P. We're given P, T, N, and R we are going to use. It's a constant. You should also be able to find it on the internet. So V is going to be equal to 625.414 mole multiplied by 0 0.0821 liter atmosphere per Kelvin mole. And this is going to be, it's at 25 plus, we want to change it to Kelvin for the sake of unit consistency. And then this is all over 1 atmosphere. So we're going to see these cancel, these cancel, these cancel, leaving us with 151,308.950 liters. And that's our final answer. So a 75-mile trip costs you 151,308.95 liters of carbon dioxide. Okay, next up, we want to balance this given reaction between magnesium and oxygen, which is actually a very bright reaction, which you should have seen in a high school chemistry lab. MgO. So right now, yes, magnesium is balanced, but oxygen is not. So to balance oxygen, we see we have 2 on this side. We need to make ourselves have 2 here. Easiest way to do that is to add a 2. Remember, you can't add subscripts. You can only add constants ahead. And so now oxygen is balanced. We have 2O, but we have 2 magnesium. And this can be balanced by adding a 2 here. And this is our final balanced equation. And that's it. Okay, next up, we want to find the oxidation state of a single bromine atom in NaBrO3. And so we need to note that the net charge is equal to 0. Again, we're going to be using conservation of charge, so you just need to note down the individual oxidation states. And so Na is in group 1, so it has an oxidation state of +1, and oxygen has an oxidation state of -2. Bromine is what we're trying to find. These will always be these 2 values. And so you just write down an algebraic equation. So +1 plus x plus 3 into -2 is equal to 0. So 1 minus 6 plus x is equal to 0. So -5 plus x is equal to 0. This means x is equal to 5. So bromine has an oxidation state of +5. Okay, for our last question. One last calculation question, and we're going to be using equilibrium, which means ice tables. So 100 milliliter buffer solution of 0.175 molar in HClO and 0.15 molar in NaClO. What is the pH after the addition of 150 milligrams of Hbr? So first we want to determine the moles of Hbr, and that will give us the moles of H plus because of its dissolution. And so it would be 150 milligrams times 1 gram per 1,000 milligrams times the molar mass, over the molar mass, which is times 1 over the molar mass. Let's just erase this line. And that's going to be 80.91 grams. And this gives us a final answer of 1.854 times 10 to the negative 3 moles. Because the ratio is 1 to 1 to 1, we have the same amount of moles of H plus. And then next up, we're going to use an ice table, but first we need to find out the initial concentrations of HClO and NaClO. So let's just note up here. Now you want to find the moles of HClO. And this would be equal to 0.175 molar times 100 milliliters. So times 1 liter per 1,000 milliliters. And this is going to give us 0.0175 mole. NaClO is going to look similar. 0.15 molar times 100 milliliters by 1 liter over 1,000 milliliters. And this is going to give us 0.015 mole. So next up, we're going to build our ice table, which is going to help us determine the concentrations at equilibrium. We have 1.854 times 10 to the negative 3, 0.015, 0.0175. You're going to use the least one in order to determine the change. So this is going to be minus 1.854 by 10 to the negative 3, minus 1.854 by 10 to the negative 3, which means that at equilibrium, we're going to have 0 of this, 0.013146, and 0.019454. Okay, and then now we're going to use the Henderson-Hasselbalch equation in order to find the pH, and we need to note down that the pKa of HClO is equal to 7.54. And the equation states that pH is equal to pKa plus log A minus over HA. So we're going to use these two, of course. And this is going to give us 7.37. And that is your final answer. Okay, and that concludes today's session. I hope you enjoyed the content that I had for you today. If you need any extra help, be sure to check out the links in the description and the OneClass page itself. This is Marlyn from OneClass. Hope to see you next time.